Here, come on, give me the right option. All right, welcome. Happy Wednesday. Hope you're having a great day so far. Things we've got going on. We're in that last content section of the first unit, which is chapter 1 and chapter 2. So this is, we have a little bit to look at for 2.4, I think still. And then 2.5, we will look at for the remainder. You have written homework due Friday. And Friday is also our review day, so come with questions or come with stuff to work on to be able to ask questions while you're working. I'll take questions first of big overarching things, and then if there's not anything you specifically want to ask about, it will be time for you to work on those many problems and preparation for the exam and be able to ask while you're working. You have post-class activity due today, which we're going to talk about one of those problems. And then we have one that's assigned today, due Friday. So any questions on things as we get going? All right. All right, we're gonna need some flexibility today. The pen I use has gone missing, but we'll still be able to figure out these things. This is not the worst technology issue I've ever had. But we were at the end of class. Did I type those wrong? Is it 2.5? Oh, okay. I saved something wrong. There we go. All right. So on Monday, we talked about continuity, and it's largely, does the function exist? Is it part of our domain? Does the limit exist? And then is the function and the limit the same at that point? It is, can I draw that function by hand without picking up my pencil? And we're down on some example problems. The last being finding the values of x at which f is not continuous, and then stating whether the discontinuities are removable or non-removable. And it comes down to, for removable, that's something where the numerator and denominator would cancel each other, and we'd end up with a simplified function that I can get rid of the issue to evaluate the limit. And analytically, that was I can factor and get rid of the problem terms. And non-removable is I can't cancel away the problem terms. They're going to remain there. So right at the end, talked about x minus 5 over x squared minus 25. X squared minus 25 is a difference of squares, factors into x minus 5 times x plus 5. If I look at what can cancel away the x minus 5s, can cancel away. So that makes 5, the thing I plug in to make that 0, removable. Whereas x equals negative 5 is non-removable. Let's actually look at that graph real fast. to see what I'm meaning by the cancel away versus can't. It was x minus 5 over x squared minus 25. Here it is. At x equals -5, we've got a vertical asymptote. Can't get rid of that vertical asymptote. But at x equals +5, over here, it looks continuous, but when I actually highlight that point, it's undefined. So the removable is, my function would look continuous if I graphed it with technology. Non-removable is, it is very obviously not continuous. Right, so let's look at another example. F of x equals x plus 2 over x squared minus 3x minus 10. How does that denominator factor? X plus 2, x minus 5. We'd have x plus 2 over x plus 2, x minus 5. What cancels away? The x plus 2's. What would make x plus 2 0? -2. So x equals -2. The thing that makes x plus 2 0. It's not continuous there, but this is a removable discontinuity. What doesn't cancel away? The x minus 5. It's still in the denominator, though, so it's still a problem. What would be making me divide by 0 in that x minus 5? Yeah, 5. So x equals 5 is a non-removable discontinuity. I don't really understand why the font changes from when I type to when I hit enter, but it does. And then last theorem of 2.4, before we get into 2.5, is the intermediate value theorem. It says if f of x is continuous on the closed interval a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in a, b, such that f of c equals k. This sounds complicated, and when I start drawing a picture, it's going to be, isn't that an obvious fact? It's saying, here I have a graph. Here is my function. Say here is A, meaning over here on my y-axis is f of A. And a little ways down, I have B. And it has its output f of B. And those two outputs are not the same. It's then telling us that any number between f of A and f of B, so say here is some number between them, there is an input such that I hit that output in between. Well, if I have to draw this without picking up my pencil, I have to go through that output of, if I pick someplace in here, I have to draw through it and get an output. So say there is a K here. That means, with a different color, going in, there is a C that hits that output. and that C is between A and B. But if I have to draw this without picking up my pencil, of course that's going to happen. There's not going to be some weird jump that skips over that point. But it does help us in cases where we need to know there's a solution to something, but we might not know where it is. So, like this cubic x cubed plus 5x minus 3. Like the quadratic formula, there is a cubic formula. It's disgusting. So we don't ever deal with a cubic formula, but we want to know if there's a solution of f of x equals x cubed plus 5x minus 3 between 0 and 1. There's some decimal solution. The intermediate value theorem says for there to be a 0, if I plug in 0 here and I plug in 1, for there to be a 0, those would need to be different signs, ultimately. So let's actually try plugging in f of 0 and f of 1. If I plug in 0, I get 0. I do have a little exponent tool. No, I don't. I get 0 cubed, which is 0, plus 5 times 0 minus 3. What is 0 plus 0 minus 3? Negative 3. And if I plug in 1, I get 1 cubed, which is 1, plus 5 times 1, 5 minus 3. 1 plus 5 minus 3 is positive 3 this time. What this is saying is this function, I don't quite know what it does, except I do know at 0, x equals 0, I hit negative 3. And at x equals 1, I hit positive 3. Somewhere between, I cross the x-axis. So somewhere in here, and we cross the x-axis, there is a solution to, or there is a 0 to f of x equals x cubed plus 5x minus 3. We could then use other tools to estimate what that 0 is, but the intermediate value theorem gives us there is something. We have crossed the x-axis because I can't go from negative 3 to 3 continuously without. Okay, so that was the last theorem of 2.4, and we'll get into 2.5. So let's consider this function f of x equals 3 over x minus 2. Using, from what we've had, 1, where would this not be continuous? 2. I can't plug in 2 because I can't divide by 0. So this is discontinuous at x equals 2. Is it a removable or non-removable discontinuity? Non-removable, I can't cancel it away. So it's non-removable. So it's going to be obvious in our graph that there is a discontinuity. So let's look at the graph. It was 3 over x minus 2, I think. And sure enough, at 2, there is no way for me to draw through this function without picking up my pencil. But we have been hinting at this idea for a while and getting to this idea in saying this idea, the limit as x goes to 2, say, doesn't exist because that left and right don't match. But also they don't go to a single value because they go to infinity. But we can talk about infinite limits in this concept of limits of when a function goes towards infinity, we can say the limit approaches infinity, and we can actually write an infinity symbol. So suppose I want to look at the left and right hand limits on these. If I look at the limit of f of x as x goes to 2 from the right, I apologize for the lack of exponents. But if I look at x as it goes to 2 from the right, I can say it doesn't exist because it goes to infinity, but I can actually be even more precise and say that limit is infinity. And then on the other side, the limit of f of x as x goes to 2 from the left. What do you think we'd say for from the left? Negative. Negative infinity. It goes down forever. So, and we've been hinting at these. We've been generally using them and talking about them. This is a formal way of saying the limit doesn't exist, but being more precise about how the limit doesn't exist. So, definition. Let f be a function that is defined at every real number in some open interval containing c. I can draw my function around c. Except maybe at c itself. Maybe I have a hole. Maybe I have a removable discontinuity. Maybe I have a non-removable. I have some type of discontinuity, possibly. We say the limit of x goes to, the limit as x goes to c of f of x is infinity, which means the closer and closer I get to c, the higher and higher my function grows. What all that m and delta and f of x greater than m is saying. The closer and closer I get to c, the higher and higher my function goes. Similarly, saying negative infinity means the closer and closer I get to c, the more and more negative my function gets. So with this graph, make that bigger. As I get closer and closer to 2, say here I am at 2.5, I'm going upwards, but as I even get closer to 2, I get even further up. And I can get as close as I want to 2, and my function keeps growing, but as soon as I plug in 2, I don't have a value anymore. What these big statements are saying. We can similarly talk about right and left-handed limits, as we already did. So let's look at the limit of these, and let's start by doing it in the table sense of, I want to look at the limit as 1 of 1 over x minus 1 squared as x goes to 1. So I'm going to plug in some x values and find out the function. So what would be some values close to x for us to try? Sorry, close to 1 for us to try. 0.9. I'm going to type 0.9. What would be closer? 0.99. 0.999. On what would I do from the other side?
1.1.
1.1. 1.01. 1.001. Okay. Why don't you guys try plugging in values and see what we get? Yeah.
0.9, I have 100.
100. 0.99. Somebody have?
Uh,
1,000.
for, for 0.999, I have 1E6.
1E6. Are we positive 0.99 was 1,000? Huh? One more zero. One more zero. Okay. What's happening as we approach 1 there?
Y gets bigger.
Y gets bigger and bigger and bigger. It's going towards infinity. Which side would this limit be?
Left.
The left-hand side is the smaller values. So this is saying the limit of f of x. I'm just going to call them f of x, even if they're not labeled. As x goes to 1 from the left is infinity. Okay, what about the 1.1 side?
It's pretty much the exact same thing.
Yeah, and it would be. If we think about what is happening, we're subtracting from 1 and squaring it, and these two have the same difference away from 1. These two have the same difference away from 1. These two have the same difference away from 1. So the fact these values come out to be the same makes sense. But then we can talk about this side of the limit. What side of the, which side of the limit would that be? These would be the right-hand side. So the limit of f of x as x goes to 1 from the right is also infinity. And the general rule is we can talk about the limit if these match. They do match. They're still, I will keep repeating, they are still a form of being undefined, but they still match. So the limit of f of x as x goes to 1 is infinity. A very precise way of saying doesn't exist. Looking at the graph, we should hope to see that on both sides, they go up towards infinity. And yeah, sure enough, both sides funnel up towards infinity. We don't have the two different direction this time. But I want to think about how we could do this without making a table, because we start getting to that point of making a table, and that gets repetitive, but it also gets long. So what can we be thinking through to justify it without having to write out values and type things into our calculator? So 1, it's discontinuous at 1. Why? Why do we know that 1 over x minus 1 squared is discontinuous? The denominator is 0 when I plug in 1. So it's discontinuous. What type of discontinuity? Removable or non-removable? Non-removable. I can't get rid of that. There's nothing in the top for me to cancel it with. So it's a non-removable discontinuity, which generally results in an asymptote. And so then I want to think through, we did this Monday, what would be the signs of both the numerator and denominator? So as I put in values close to 1, well, the numerator is always positive. All right, 1 just stays fixed. That's always positive. But what do I get when I divide by, well, sorry, what happens when I square a number? What is the sign of something squared? Positive. I'm squaring my denominator. My denominator is always a positive number. So even though I'm dividing by 0, at 1, I have a denominator near 1 that's always going to be positive. Positive divided by positive is that is why all of these are positive infinities. It's a non-removable discontinuity that's always positive near 1. So let's look at another one. Oh, I did get it fixed. I had a typo before. Okay. Without doing a table, I want to look at each little limit as we approach 1 from each side. So let's do the right first. So what types of numbers near 1 would we be looking at? Bigger numbers near 1 or smaller numbers near 1? Bigger, things that are bigger than 1. So our 1.1s, our 1.001s. Okay, so if I take 1.01 minus 1, is that a positive or negative number? One 0.01 minus 1 would be a positive number. So right now we'd have a positive, and the numerator is always negative. It's discontinuous at 1 because if I plug in 1, I get 0 in the denominator. It's a non-removable. I can't cancel that away in any way, shape, or form. I can't cancel the x minus 1 away. And now, when I look at my signs, I have the two things I just noted, backing up a sentence. The fact that it's discontinuous and it's non-removable indicates we're going to have a positive infinity or negative infinity. Looking at the signs, is it positive or negative infinity? Negative. Negative divided by positive is a negative. Oh goodness, that f of x has seen some better days. Negative infinity. What about from the left? Those first two bullet points I have of it's x equals negative 1, or sorry, x equals 1 is a non-removable discontinuity, remains the same. But now, from the left, are those values bigger than 1 or smaller than 1? Smaller than 1. So that's our 0.99s, 0.999. If I take 0.999 minus 1, I get a positive or negative number. I get a negative number. So my numerator is still negative. My denominator is negative. What's a negative divided by negative? Positive. So is this limit going to go to which infinity is it going to go to? Positive infinity. And hopefully our graph defends that. So we have -1 over x minus 1. Note to self, just keep a parenthesis there and it will keep it bolded. From our notes from the last side, from the left, which one did we have? It was going to positive infinity from the left. Sure enough. From the right, it was the other. It went to negative infinity. The graph matches. It defends what we just did without one needing to put in a whole bunch of values. Just using some logic of what will the signs be to figure out if it's positive infinity or negative infinity. Okay. We've been using the word, but the actual definition of a vertical asymptote is based around limits. If f of x approaches infinity or negative infinity as x approaches c, that is quite literally the meaning of a limit, from the right or the left, then the line x equals c is a vertical asymptote. So if either side goes to infinity or negative infinity, we have a vertical asymptote. Let f and g be continuous functions on an open interval. If f of c is not 0 and g of c is, then there exists an open interval containing c such that g of x not equal 0 for all x not equal to c in the interval. Then the graph of the function h of x equals f of x over g of x has a vertical asymptote. What I want to note is this line. This line is the two things we were checking with all of those limits. That statement here is the point C is a non-removable discontinuity. If both f of c and g of c were both 0, that's the situation where we could cancel it out and it would be removable. But this statement is saying c is a non-removable discontinuity. We can't cancel it out. And in that case, we then have a vertical asymptote at c. Whether it goes to positive or negative infinity, what we can then do with our limits. So we have an example here. H of x is 1 over 2 times x plus 1. Where is there a vertical asymptote? Where is the denominator undefined? -1. I can't plug in -1 because I have 2 times -1 plus 1. 2 times 0 is 0. Can't have that. X equals -1 is a vertical asymptote.
And why was it we can't have?
Hmm?
Oh, -1?
Yeah. Do I need to put spaces in?
No, you're good.
Okay. I know the typing font is a lot weirder because it also, I don't know. Yeah. Sometimes the PDF does this as well, where it just drops off words that I wrote. It's a vertical asymptote. I might try and, no,
If it's a touch screen,
it's not.
okay, then
I appreciate it. That's why I have the thing that I plug in.
yeah.
It's not a touch screen. I appreciate the offer. So it's a vertical asymptote. Then additionally, If we wanted to sketch a graph of this, we know at -1 we have an issue. On each side, what will this graph end up looking like? Will they be going to negative infinity or positive infinity? So first, if I plug in values smaller than -1, so like -1.1, what sign will that function have? If I plug in things like -1.1. The whole thing will be negative. Because -1.1 plus 1 is still negative. And I have a positive divided by a negative, so it'd be negative, meaning our function does something like that. What about if I plug in values smaller than -1? So like bigger than -1 to the right of -1. So like negative 0.99. I'd put negative 0.99 in for x. Is the whole function positive or negative? The whole thing's positive. So our vertical asymptote, our function, without even going over to the graph, we know is going to look something like this. Might as well. It's the one place I can actually make things look nice. Hey, cleaner than what I drew, but it looks the same. Get them side by side. Essentially, same thing, and we got there with just thinking through what would the signs be on each side. All right, let's look at g of x. That's not what I'm trying to do. This is what I'm trying to do. G of x. X squared plus 2x plus 1. Let's first answer the question of where are there discontinuities. What values can I not plug in to that denominator? I can't plug in 1, so there's going to be x equals 1. Anything else I can't plug into the denominator? I can't plug in -1 either, because -1 squared is 1. 1 minus 1 is 0. So x equals 1 and x equals -1. Now, which one are they both vertical asymptotes? Is it going to be one or the other? I'm gonna go up to this definition, and it's the C is non-removable, meaning I can't cancel them away. So we can, try plugging them in. So first, let's try plugging them in. If I take 1 and plug that into the numerator, what do we get when we take 1 and put it into the numerator? 4. That's not 0. Our definition says if the numerator is not 0, but the denominator is, that's a vertical asymptote. So numerator is not 0. Denominator is, this one's a vertical asymptote. Okay. X equals -1 was our other. If I take -1 and I plug that in to the numerator, what do we get when we plug -1 into the numerator? The same? Mm-hmm. -1 squared is 1. 2 times -1 is
2.
-2. So we have 1 minus 2 plus 1. 0. Our definition says the numerator is not 0, and the denominator is. We already know the denominator is 0, but we just saw the numerator is not. So this is not a vertical asymptote. What it is a removable discontinuity. And we can see that using our methods from before. How does that numerator factor? I heard it very quietly. It's x plus 1, x plus 1. All right, 1 times 1 is 1. 1 plus 1 is 2. How does the denominator factor?
Plus one, x minus.
X plus 1, x minus 1. We are talking about college algebra. This is basically all we've been doing. A lot of this. What cancels out of the denominator? The x plus 1 cancels with one of the ones up top. X equals -1 is a removable discontinuity. What doesn't cancel from the denominator? X minus 1. X equals 1 is a vertical asymptote. Vertical asymptote and the non-removable discontinuities end up being the same thing. Right. Cosecant. What is another way for us to write cosecant? It's 1 over something.
1 over cosine. No, 1 over sine.
Are we confident?
Yeah, 1 over sine.
Okay, I had how to remember them.
It's cosine. Cosecant is sine.
The C's and S's switch. So it is sine. C's and S's switch, and then cotangent goes with tangent, which is pretty much the obvious one. But for cosine and sine and cosecant and secant, the C's and S's switch.
The one thing I have memorized.
All right. So, there's not really a way to rewrite this to make us not divide by 0 occasionally. But we're going to end up dividing by 0 because sine of x can be 0. When can sine of x be 0?
When sine of x is 0.
And what would x be in those cases? 0 is one of them.
Not a number upper than 0.
There's an infinite number of them.
Oh.
Okay, sine goes with what coordinate on the unit circle? Okay.
Sine.
So here is sine of 0.
What?
Here it crosses, y crosses the x-axis again. What would be halfway around the circle?
Pi.
Pi. What would be another halfway around the circle? 2 pi to get all the way around the circle. Do we see a pattern? Could we make a guess at the next one?
4 pi. No,
You're
that's
skipping one. The next one would be 3 pi. Sine of x is 0 at multiples of pi.
0 pi.
No, that's one. We could keep going, but what I just said, sine of x is 0 when x is a multiple of pi. So I'll write that as k pi. These are all non-removable. You can't cancel it out in any way. So these will all be vertical asymptotes. So I want to, look at the graph of sine of x. If I can type it correctly. There's sine of x. Here's sine of x is 0. Here is, if I can get close enough to it,
So 3.14.
3.14, that's approximately pi. 2 pi is 6.28. Approximately in there somewhere. I wish Desmos used pi. Well, it does, but not in the way I'm wanting it to. But there's all of our zeros. The graph of cosecant should have vertical asymptotes at each spot this crosses the x-axis. They're a little hard to see because they're separated from each other, but sure enough, that's exactly what happens. At 0, here is our vertical asymptote going down and the other side of it going up. At pi, up, the other side's down. We could figure out the signs if we worked hard with our trig knowledge, but ultimately the big thing is where are the vertical asymptotes was what the question was asking. All of the vertical asymptotes of cosecant are at those zeros of sine. And the zeros of sine are the multiples of pi. All right. Yes.
So that's for a vertical asymptote. It's the numerator is 0 and the denominator is 1. What about a horizontal?
There is a definition for it. We're not getting to them here. The reason I'm reaching for the book is trying to figure out where we do get to them. There are rules for them. And it's based on the powers. Yeah. Just real quickly. If I have x, I'm gonna use carrots, but 3x squared cubed minus 2 over x squared plus 8. It does not need to be complicated. Okay. Horizontal asymptotes. We will get to this eventually. So it's if the higher power is in the numerator, there is no horizontal asymptote. If the higher power is in the denominator, so say we flip this, the horizontal asymptote is 0. And then if the powers are the same, so say, it's not what I wanted. Say this was at 3x to the 4th plus 8. The powers are the same, it's these coefficients. So 1/3 be the horizontal. I know we will get there, just not in this section, but there is that rule. It is the higher power. Infinity if the higher power is in the numerator. 0 if it's in the denominator. If they're the same, it's the coefficients. All right. Back to these though. I want you guys to try these. Finding each of these limits. It's the same function. You just need to find the left and right hand limit of these functions. I What's the limit of the top one?
Positive infinity. Oh, like numerator.
The whole thing. When I say top one, I mean there's two on the screen. The top limit. Why positive infinity? It's going to be a negative over a negative because when we're looking close to 1 squared minus 3 times something close to 1 is going to end up being negative. Like 1 minus something close to 3 is negative. The denominator, when I'm on the left of 1, that's the 0.99s. 0.99 minus 1 would be negative. Negative over negative is absolutely correct. Positive infinity. What about the second one? Negative infinity of, if I did, the same logic applies in the top. X squared close to 1 is close to 1 squared, which is 1. 3 times something close to 1 is close to 3. Something close to 1 minus something close to 3, gonna be negative. But now we're taking something bigger than 1 and subtracting 1. That's going to be positive. And so negative over positive is negative infinity. Right. Had a question. Which of these is going to change if I square the denominator? The denominator becomes squared. What's going to change? The top one, y. When I square a negative, it becomes a positive. I'd have a negative divided by a positive, which would be a negative infinity in our alternate reality case. In this one, square a positive is still positive. That limit stays the same. So it's not always one's going to go one way and the other's going to go the other. They do go the same direction. We've seen examples of that already today, but one of those paying attention to not always one direction and the other. It's looking at their sign, big picture. So then we get a list of rules. And ultimately, once again, whenever we get these list of rules, by and large, they're gonna act the way we think they're going to. So say the f of x goes to infinity, but g of x goes to some finite number. Well, if I take infinity plus a finite number, that's still infinity. And if I take infinity minus a finite number, that's still infinity. F of x times g of x, if I take infinity times a number, it's still going to be infinity, but I put a plus minus there. What do you think the plus minus is for? What's going to determine plus or minus, I guess is what I mean. So which thing is going to be positive or negative? The finite number, the limit of g of x. This depends on if L is a positive or negative number. So if L is negative, infinity times a negative will become negative. And then if I divide by infinity, if my denominator becomes really big, it approaches 0. So examples, The limit as x goes to 0 of 1 plus 1 over x squared. Practicing from before. Nope, gonna try and type. Gonna try and type and actually type. Limit of 1 as x goes to 0. Plus the limit of 1 over x squared as x goes to 0. I'll add in a denominator, or not a denominator, but a fraction bar. If I break it into the two limits, is what I'm trying to do. What is, practicing our limit rules, the limit of 1? 1. What is the limit as x goes to 0 of 1 over x squared? No, if I've heard it. Huh? It's gonna be positive. Positive what? Infinity, because we're dividing by 0 and we're dividing by a non-removable 0. And 1 over something squared is positive, so 1 plus infinity. I don't know if these childhood fights still take place, but the ones of like, I did this times infinity. Well, I did this times infinity plus 1. Infinity plus 1 is still infinity. So the limit as x goes to 0 of 1 plus 1 over x squared is still infinity. All right. Think about some trig. All right. We have the limit as x goes to 1 from the negative side of x squared plus 1. I can take the limit of the numerator and denominator generally to figure out what this is going to be. So first, what's going to be the limit as x goes to 1 from the negative side of x squared plus 1? It's positive. In particular, we know what that number is going to be. It's going to be 2. The numerator goes to 2 because I can plug in 1 to this and be just fine. The numerator goes to 2. 1 squared plus 1 is 2. It's that denominator part. We have cotangent. What is cotangent in terms of sine and cosine? It's 1 over tangent. So what is tangent in sine and cosine? Tangent is sine over cosine. So cotangent is the reciprocal of that. Cotangent of x equals cosine of x over sine of x. Okay. When I get close to 1, that means I'm getting close to pi inside of here. What is cosine of pi?
1. Or -1.
Negative 1. What is sine of pi? 0. So we have a fraction dividing by 0. Which means the limit of this is with pi's in here. The limit of this one Dividing by 0. I can't get rid of that dividing by 0, meaning this is going to be a positive or negative infinity. The whole thing we've been having all day. This is a positive or negative infinity in the denominator. Want to figure out which one it is because it would matter. So let's think about it. We're approaching pi, right? Pi times 1. From the smaller side of 1. So on our unit circle, we're here-ish. We're coming in towards pi, but we haven't reached pi yet. That's what the smaller side of 1 in here is saying. What is the SIGN sign of cosine in this quadrant? Is cosine positive or negative there? It's negative because cosine is x, and on this side, x is negative. Is sine positive or negative here? It's positive because it's above our x-axis. We haven't quite reached the other side. So we still have positive. So we have a negative over positive infinity, meaning which infinity? Positive or negative? Negative infinity. So ultimately we have 2 over negative infinity. I'm not going to be grumpy if this is written. 2 over negative infinity. That's this last rule. If I have something over infinity, it's 0. So the limit of this becomes 0. That one's actually one would be good to look at because that looks like a funky graph. X squared plus 1 over cotangent of pi x. And that was what we had, cotangent pi x. Squared plus 1. Oh, I'm looking, expecting it to hit here. Here's 1. And sure enough, we cross the point 1, 0. Right. Someone's important for us to note. Limit as x goes to 0 plus of 3 natural log of x. Okay. Ooh, yikes. What does the graph of the natural log of x look like?
One of those goofy goofers that like kind of.
I mean, they're all kind of goofy goobers. But what were you drawing with your finger? Generally the right shape. It's the inverse of what function?
The inverse of the x.
It's the inverse of the exponential. What does the exponential look like? Yeah, it's flat and then goes up. And so what was being drawn up here, I should do something maybe other than red and orange. Let's do red and blue. Is the blue is our general shape of an of the logarithmic. So 3 times the logarithmic is just going to stretch it more, which I don't have any scaling on here. Here's our graph of 3 times the natural log of x. What's the limit as x goes to 0 from the right? Negative infinity. One of those. Recognize the graph, and we can see very quickly that's going to be going to negative infinity. We can't, however, talk about the graph, the limit from the left-hand side here, because there's nothing on the left of 0. So this problem is very specifically from the right because there is nothing on the left. We can only talk about that right-hand limit. So one of those, watch your negatives. And at least one more here. The limit as x goes to 0. From which side? Left. Those are gonna be what type of values? Smaller. What values are trying to figure out how to phrase it. On a number line, the values on the left of 0 or smaller than 0 all have a property. What are those numbers? They're the negatives. So we're looking at what if I'm plugging in something close to 0 but negative. Limit as x goes to 0 of x squared is not just a sign. We can evaluate this one. So it's not even necessarily, I mean, yes, close to 0, positive. At 0, we can evaluate that one. That is 0. So this equals 0 plus 1 over x, the limit as x goes to 0 from the left. What would the denominator be? Plugging in 0 from the left, can I plug 0 in?
No.
No. So I need to think about what happens when I divide by 0. When I divide by 0, if I can't remove it, I get infinity or negative infinity. So now, am I going to get positive or negative infinity? We'll get negative infinity. And ultimately, it's negative infinity because especially if I add any finite number to infinity, it stays infinity, but especially if I add 0. So we have all of our infinite limits of going to infinity, not eventually. I am sure we will talk about if we have an infinity here. So be prepared for it to come back, just not in this unit. All right, so that is end of this section and end of the first unit. So again, you have a post-class activity, which is, if I type it correctly, should be one of the problems we've done today. We'll have a review day. Come with questions or come with something to work on. Questions first, able to work on things later. And we'll look over stuff. Then if you have any other questions, also your homework 3 would be due on Friday. So if you have any questions, let me know. Have a great couple of days. See you Friday.
Oh, Kristen, this is the second pencil I found. That's not the same one that, that's a different